Welcome to EE online series. In this class, we are going to be talking about resistance and Ohm's law. Though we've discussed about resistance in our previous class, we were made to understand that resistance is a particular component, electrical component that resist or impede the rate at which current flows into the circuit. So this time, we're going to be correlating it, the applications of resistance and Ohm's law in the electric circuit. So, for example, let us take water current as an example, again to explain the resistance. So, what will happen when you throw some rocks into a small creek? So, let's say, for example, you have a passage where water flows through. So, if you throw a little rock inside it, what will happen? So, we notice that the rate or the speed of the, or you say current of the water will reduce or will be uh, stopped, or sometimes it can come down. So we will notice that the rate or the speed of the water will slow down. This is because the rocks, which serves as the resistance, will slow down or resist the flow of the water. So a similar concept also be used in electric circuit as well. So we regard this as a resistor, which causes resistance or current resistance. So what they do is they resist the flow of electrical current. So the higher the value of resistance, the smaller the current be will be. So the resistance of a conductor is a measure of how difficult it is to resist the current which flow in a particular circuit. So this is what we are talking about here. These are the two terms in play. So we are looking at the resistance, which is the capability or the uh, ability to resist or stop the rate at which current flow into a circuit. And on the same hand, we have resistor. So resistor, a two-terminal component of a circuit that limits the flow of current. So we should take note of these two. They are very important thing we need to understand. So they both have the same symbol, which is RR. So the resistor is the component itself, which that limits the flow of current, while the resistance is the ability or the measure of a material's opposition to the flow of current. I think that is well taken. So now, let's look at the symbol we can use to recognize whenever we come across a resistance in a circuit. So exactly what we have here. So we have two types of resistor. We have what we call fixed resistor. So it can either come with this symbol or it comes with this symbol. So the other one we have is variable resistor. So variable resistors always be with the same symbol, but it has one a arrow that pass through it, and the same thing as came to this. So the arrow is either pass through it or it will be in this form. So these are the two symbols we can use to represent or to denote resistor in a particular circuit. So now, away from the symbols of the resistor, let's quickly look at the factors that affect resistance in a particular circuit. So when I'm talking about some factors that affect resistance that can have some negative or positive impact on resistance. So we have a lot of things to talk about here. We have the what we call the area. We have the temperature. So the length of the cord, resistivity of the material. So these are the four major factors that affect resistance in a circuit. So we have area here, we have temperature of the material, we have the length of the conductor L, and we have resistivity of the material. And this is a symbol in form of um, P here. So it is known as rho. It's known as rho. It's a Greek letter. So we can represent all these things now for better explanation. We can represent in a particular diagram I'm going to give you right now. So here is example of what I'm talking about. So we can use this whole diagram to represent the factors affecting the resistance in a particular circuit. So the first thing we are looking at is the area. So when you look at the area, so it has a very what negative effect on a particular uh, circuit. So it's just like when you have more water that flows through a wider pipe than that through a narrow pipe. So you will notice that the larger the diameter of the wire, the greater the um, cross section, cross sectional area, greater the cross sectional area. So what do we mean? It means that if we have a pipe, a particular water pipe that is very wide as possible, so we notice that more water flows easily through it. So compared to a narrow pipe, so the current that flows through a narrow pipe, you cannot compare it to the one that flows through a wider pipe. So more water flows through it. So which means the larger the diameter of the wire, the greater the cross sectional area, and the less the resistance in the less the resistance in the wire, and the more the current that flows through the conductor. So if the resistance is little, definitely the rate at which current flows through the conductor, it will be very fast, just like we have in what uh, in a wider pipe. As water flows through it, the water will be very fast, so the current will increase. So now the second thing we are looking at is the length of the conductor. So the length of the conductor is also it also determine the rate at which current flows through a particular conductor, or the wire. So which means if the length is very long, definitely it will take time for current to pass through them. So if we have too much of length, so which means the longer the wire, the more the resistance, and time taking the more the time taken for the current to flow through it. So if the wire is too long, definitely resistance as well will be so long, so it will take time for current to flow through this particular conductor. So the next thing we're going to be talking about is the resistivity, which is what we have here. As I said earlier, I said it is known as rho, resistivity. So in case of resistivity, so as a matter of fact, resistivity varies in materials or in conducting materials. So which means resistivity has to do with the measure for the opposition of flow of current through a material of wire, or how difficult it is for current to flow through a particular material. So the different materials have different resistivity. That is what it means. So more or less resistance in the materials. So it's when I'm talking of resistivity, it depends on material. That is what it is actually written here. So it depends on the material that we allow the current to pass through them. So we can talk of metals like iron, like aluminium, and so on and so forth. So resistivity varies in them. So some have higher resistivity than the other. So that is all about resistivity. So the next thing we are going to be moving to now is the um, temperature of the wire. So let's look at temperature. Oops. So when I'm talking of temperature, resistivity of uh, of a material is dependent upon the temperature surrounding the material. So resistivity increases with an increase in temperature for most materials. So as the temperature of materials increase, definitely the resistivity as well also increase. So now let's take a look at some examples of some materials with their resistivity. So value of their resistivity, or sorry, the temperature, So let me just look at the one we have here. So excuse me, we have copper on this list. We have copper with resistivity of what, of 1.68 times 10 raised to power minus 8. We have gold as well, 2.44 times 10 raised to power minus 8 as well. We have aluminium, we have silver, we have iron, as well as a tin. We still have some other metals like that. So we have nichrome, we have lead, we also have a brass as well. So all these metals has their what, has their resistivity, and what they call it, that should be in home. That should be in home. ohmmeter. So they all have their resistivity and the temperature, and we've also said that resistivity of a material is dependent upon the temperature as well that surround the material. So which means the resistivity is the one that will determine the temperature of the material as well. So it seems the two are a little bit related. So that is that about the temperature and resistivity of a material in relations. So now let's go back. So the other one we still have is what? Okay, I think we have already covered the whole thing. We talked about the area, the temperature, the length of the conductor, which means where the as long and the longer the wire, uh, it takes time also for the wire to for the current to flow through the wire. So it means if the wire is long, definitely the current will also be slow. We have a little amount of current that flows through it. So we have resistivity of the wire and the temperature as well. They are the same thing. We've related them. So factors affecting resistance can be mathematically expressed with the following formula. We're going to take a look at them. I said the one that really relates them together is resistivity. So resistivity is, let's say, start with R because rho, please don't mind my rho, length over area. So that's length over area. So this is the relationship between them. So where where A is the cross-sectional area of the conductor, and L is the length, and the temperature as well stands for T. We already know that, and this is rho, which stands for the resistivity, uh, which is the conductibility of a material for a wire. So that is that concerning the relation of resistivity. So here is an example to take note under resistivity. So we have there is a copper wire 50 meter in length with cross-sectional area of 0.13 centimeter square. What is the resistance of the wire? So I think that's a simple question we need to look at under resistivity. So in our former discussion relating to uh, temperature, which is one of the factors of factors that affect resistance in the conductor. So we talk about temperature and their resist and in relation to resistivity. So we made mention of some factors and their so we made mention of some metals and their resistivity. So what do we have now? So I think we have this. So we have this. So we talked about what? We talked about copper. So I think that's the metal that was given in the question. So that is we have copper. So we are going to take note of all the parameters given now. So according to this question, we have our length given to be sorry. I think I was using a black pen before. So sorry, we have the length given according to the question to be what? To be 50 meter. To be 50, sorry, 50 meter. So the next thing is what? We're given the cross-sectional area as well. So the cross-sectional area given, which is our A, is equal to what? 0.13 centimeter square. So what next on the agenda? We have what do you call it? So now we need our resistivity this time around. Our resistivity. So from what we can see from our earlier given, we have the resistivity of a particular of a copper to be what? To be 1.68 times 10 raised to power minus um, 8. So I think that's what we're going to use. Our resistivity of the copper, which is what we're given the question to be what? 1.68 times 10 raised to power minus 8. Don't forget the unit is ohm meter. So that is that. So according to the question, we are using centimeter. I'm sorry, we are using centimeters. Ohm centimeter in this case. So that is for copper. That is for copper. So now What is next now is for us to bring out our relation, which is the mathematical relation of resistivity, which is what we were given in the first place, which is R equal to resistivity rho, sorry, L over area. So if we are going to substitute all this formula inside this particular equation, we are going to have. So sorry, don't forget, um, we were given our length in meters, so we are going to convert it to centimeters. So which is going to be equivalent to uh, 5,000, right? 5,000 centimeters square. So we shouldn't forget that. I think that escaped my mind. So we are going to put that here. We are going to have 5,000 centimeter. So over the value of our area, which is 0.13 centimeters square. So I think this time around we're going to need to punch our calculator this time around. So this is what we're going to have. We're going to have 6.461538462 times 10 raised to power minus 4. So I think we are going to I'm going to shorten this one way or the other. So we are meant to have 6.462, if you like, in three decimal places, times 10 raised to power minus 4. So our unit is going to be in ohm, because that's the resistance of that particular wire, copper. So that is that on the resistance of copper. So which means if a particular copper wire is having the length that is as long as 50 meter and is having the area, which means what, the the wideness of the wire, is equal to 0.13 centimeters square. Definitely, with the same what they call amount of resistivity, definitely this is what we are going to have as the resistance of the particular wire. This will be the equivalent capacity of the wire to resist the flow of current in the circuit. So that is all about this calculation. So now, instead of having something like this, though this is applicable and is okay, so and what if we need to measure? Is there any way we can measure the resistance of a particular resistor in a conductor? Of course, there is. So we have a particular device we call ohmmeter. So that is what we are going to quickly discuss right away. So we have what we call ohmmeter. So ohmmeter is an instrument that can be used to measure resistance in a particular wire conductor. So in measuring the resistance of a resistor, so we said we can make use of ohmmeter. So if we are going to do that, then we are going to have a simple circuit like this. And so what are we saying? Before we do it, we have to make sure we remove or disconnect. So let's fully complete these circuits. So we have these, So this definitely look this way. So so what do we have here? We should have a resistor here. So sorry for the late drawing. So while our home meter will be connected across it, here. So this is exactly what it's going to look like. So we are going to disconnect it from the circuit. This is like a joint or a junction where they were disconnected. So this is our resistor. So if we are going to measure the resistance of the resistor, we are going to not disconnect it from the circuit so that we can take the readings alone. So that is the um, way of measuring the resistance of a particular resistor in a conductor. So we say it's measuring resistance with an ohmmeter. So that is what we have here. So we disconnect the resistor from the circuit, so we can easily take um, the measurement. So I think that is simple comparing to the normally when we are doing the process by which we have to know the length of the conductor, find the cross-sectional area, and so this has already what give a shortcut to that. So the next thing we are going to be looking at now is uh, when we're talking of resistance, so there should be something that can be as an opposite of resistance. So we are looking at we have conductance. That is the next thing we are going to quickly talk about now. Conductance. Don't forget that we are still going to Ohm's law. So Ohm's law and resistance, they have something um, very funny in common. We are going to take that very soon. So quickly, what do we mean by conductor? Sorry, conductance. So we can see conductance is the opposite of resistance. So which means ability for material to conduct electricity. So we can see conductor with a symbol G. Let's give it the symbol G. Is a term that is opposite to the term resistance. So it is the ability of a material to pass current rather than resist it, or uh, how easy rather than how difficult it is for current to flow through a circuit. So that is what conductance actually mean. So conductance is the conductivity of the material. The less the resistance R of the material, the greater the conductance G. So the better the conductivity of the material and vice versa as well. So when I'm talking of conductance, is the reciprocal of a resistance. So we can say mathematically conductance can be represented as so uh, the reciprocal. Excuse me. You can say conductance is going to be the reciprocal of resistance. So what does it mean? It means if we remember, we said our resistance is going to be our uh, what do you call it, rho, which is resistivity, increase in length with reduction in what, in area, cross-sectional area. So in case of conductance, now what we are going to have is going to be different. We are going to have G equal to E over rho L. So which means um, for us to have a good conducting material, the uh, area have to be what? Have to wide. The cross-sectional area have to be wide, and the length has to be short. So that's allow free flow of electric current in a circuit. So that is what we have there. So which is R, which is really the reverse of this, the reverse part of this. So therefore, conductance G is the reciprocal of resistance. G equal to 1 over R. That is the reciprocal of resistance. So that is all about conductance. So this would now take us to what we know as Ohm's law. So here we are, Ohm's law. We're talking of Ohm's law. As a matter of fact, Ohm's law is a very important and useful uh, equation in electric circuit theory. It precisely expresses the relationship between current, voltage, and resistance with a simple mathematical equation. So the equation is simply given as V equals I R, or I equals V over R, or R equals V over uh, over so, over high. So that is that for the three relations that can be found under the particular law. So, and this one can also be expressed as I equals to E over R. As we have explained in our previous class, we said voltage can also be known as what energy required to move a current from one point to another. So it's also an energy. I think that is okay. So any form of energy conversion from one type to another can be expressed in this way. So which we can also be we can also relate it to um, let's say effect. Let's say effect effect equals equals cause over opposition. So what does this mean? So we are relating this formula to this. So what does this mean? It means in an electric circuit, it is the voltage that causes current to flow, as we know, because it's the voltage that causes it to continue to move in a. It's the energy that makes the current to flow. So current flow is the result or effect of voltage. So current, the rate at which current flow is the effect of what? Of voltage. For a current to flow, so what causes it is what we know as what? As a voltage. So and resistance is the opposition. So this can be regarded as the opposition. So evidently now, so which we can relate these three terms to our current. So our current equals voltage over resistance. So these are the two relations which we can have under this. I think that is well, well, well taken. That is well taken. So thank you very much. So therefore, we can say Ohm's law expresses the relationship between current, voltage, and resistance. That's the first thing we can see now. And we can also say I through a conductor is directly proportional to V and inversely proportional to R. So that is the what we can denote from this equation and from the Ohm's law. So uh, we have I is equal to V over R, or I is equal to E over R. So from what we can actually get here. So in short, that is the what is what these are the two deduction we can get from the law Ohm's law. So Ohm's law states that the current that flows through a metallic conductor is directly proportional to the voltage and inversely proportional to the resistance. So provided the temperature remain constant. So that is all about Ohm's law. So, and again to relate conductance to Ohm's law. So we can relate conductance to Ohm's law as well as we relate conductance to resistance the other time. So if we are going to relate conductance to Ohm's law can be written in terms of conductance as well. So we are going to have what we are going to have here. We are going to have I equals GV. So since we said that G is equal to inverse of R, and we also said I is equal to V over R. So this will be the what? This will be the conductance form of Ohm's law. So now we are going to look at the application of a Ohm's law in real life. So where or in which component of electrical appliances can we apply Ohm's law? So application of Ohm's law and resistance. So how is Ohm's law and resistance applicable in our everyday life? So in most cases, the application of Ohm's law is used when building electrical devices. Most appliances will need we make use of at home. So we normally apply Ohm's law and resistance there. So these are the few we are going to talk about and many more. So the first one we have conventional domestic fan that we have at home. So we can control the speed of the fans at homes by moving the regulator to and fro. Here the current flowing through the fan is controlled by regulating the resistance through the regulator. So a circular knob on the component can be rotated to achieve a variable resistance on the output terminal for any specific value of input. We can calculate the resistance, current, and those and moreover the power flowing through the through Ohm's law. So not only that, in the second one we are talking about is electric heaters. In our electric heaters as well, they are the common appliances used in winters throughout the world. So the heaters have a metal coil which has high resistance that permits a certain amount of current to flow through them to provide the required heat. Also, the power to be supplied to the heaters is calculated using the Ohm's law. So the next one we can also say now, we can also talk about electric kettles and our present iron and tone. So the electric kettles and irons have a lot of resistors in them. The resistors limit and the amount, so the resistor limit the amount of current that flows through them to provide required amount of heat we needed, or we need to iron or to boil our water or whatsoever. So the size of resistors used in them is determined by using Ohm's law as well. So we can also talk about so that is we are through with that. We can also talk about design of electric devices. So in design of electric devices such as um, laptop and mobile phones require a DC power supply with the specific current. So many devices need a certain amount of current and voltage to operate. So these are one of the examples. So Ohm's law tells us the amount of resistance we need to establish a certain current with a certain amount of voltage as well. So the next one is the next one is a fuse infused design. So fuses are the protection component that limit the amount of current flowing through the circuit and to establish a certain amount of voltage. They are mostly connected in series in a particular device. So Ohm's law is used to figure out which resistors are needed. So I think that is well structured. So the next one is our mobile laptops and charger that we normally use in our everyday life. So I think mobile and laptop chargers use DC power as well. They use DC power supply in the operation. So DC power supply provide a variable output voltage based on the resistance, and the overall working is controlled by also by Ohm's law as well. So all these and many more are the real life appliances of Ohm's law and resistance in our appliances at home. They all have resistors in them. So it is Ohm's law we use to regulate the amount of power, the amount of heat we need in all of these gadgets. So that is all about the resistance and Ohm's law. So thanks for watching. You can easily help, or to get more of our video you can subscribe to our channel and like our video. You can also share so that you can get more of our video. Thank you for watching once again. Goodbye.